Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To speak here at Microsoft. I'll talk about a few topics we've been working on. Is my mic on? Anyway, I think it's a small room. Yeah, in the area of point-based modeling and simulation. So the starting question for this kind of work in my mind was this kind of vague question: what is the shape of a set of points? And I mean this question in sort of two ways. One can be the analytic way, where essentially I have some hidden object that I really don't know, but I just have samples on its surface. And then from just knowing the samples, I want to understand what the object is, something about the object. But also when I talk about this in a synthetic sense, namely I want to have a model of an object that itself is just a bunch of points, just a bunch of nodes. Because sometimes the way we know the shape of an object is not just from the geometry, but also from interacting with it, from squeezing it and seeing what happens as we apply some physical forces. As background, I get interested in this because I think that as we look ahead into the next 5 or 10 years, we'll be in a situation where lots and lots of shapes around us will be digitized. Already, most manufactured products start their life as a CAD model, i.e. in digital form. But I think we'll have the situation where almost every object that matters to our economy and life will also exist in digital form, including our houses, our furniture, our bodies, our organs, and so on. And as we deal with this, plethora of digital shapes, we need new tools for understanding and organizing and manipulating the shapes. And in this context, point clouds or point-based representations are interesting because they are often what a technology that acquires the shape from the physical world gives, like a scanning technology. So the overall goal of this work and some other things that I will not talk about is to, first of all, take point cloud data, take this kind of just a bag of points and try to make it into a first-class geometric models for geometric modeling. And again, to be now very concrete, what I mean by point cloud data is just a set of unorganized points sampled from the surface or the interior of some object. It's just a bag of points that have no structure. In particular, I don't have a mesh there. I don't have essentially a geometric manifold, which precludes me applying a lot of the algorithms that are known for geometry processing on meshes or manifolds. And also, unlike, say, other sample data, like audio or images or video, this is not regularly sampled. These samples are not regularly spaced in space on time. They're kind of haphazard. And so that makes a lot of the signal processing techniques difficult to apply in this setting as well. And as I said, I'm interested in this because a lot of the processes that acquire shapes, that's what they give you. Now, in the stuff I'll talk about, I'm not really just interested in taking the points and constructing a surface model. I mean, there's been lots of work on defining continuous surfaces from a set of discrete point samples. I just show here an example of a surface that was reconstructed by using the many variants of the moving least squares method. There's also been lots of work on kind of direct rendering from a representation like this. But I'll be more interested in, for example, doing synthesis using point-based physical models. That is, doing physical simulations where there is no mesh either for the surface or for the interior. There's no FEM. There's just these nodes. And actually, throughout the, and later on you will see this distinction between points that model the interior of the shape and try to capture the physics. I call this pixels, physical elements, and points that try to model the surface and capture more of how the object appears and how the object interacts in a haptic sense. And I'll call this surface. And of course, the pixels have to be coupled to the surface. So really, the second goal of this work is to make point cloud data also a first-class physical model. And there's always this debate: do you need the mesh? Is it better to have a mesh or a point cloud? And there's no one-bit answer to this question. It really depends in the context. They are both at their place. In many ways, they're equivalent. But there are some settings where point clouds make a lot of sense. That's especially when you have highly dynamic situations, like collisions and contacts, large deformations, fracture and plastic behavior. And then the point cloud is a good representation because somehow the mesh doesn't get in the way. That's the kind of situations where you have a mesh, you would have to do very large-scale updates with the mesh structure to maintain consistency. In the point cloud, somehow the connectivity is implicit in the positions of the points. And you're able to do things like dynamic resampling, namely add points where you need them, in the case of large deformation or fracture, for example, and also generate implicit surfaces that represent the surface of the object in such a way, for example, that when you have like a large area contact, you have exact agreement of what the surface is from both sides, which is very hard to do with meshes. So this talk, I wasn't quite sure what to cover, so I chose 3 different topics. I'll cover each of them briefly, so I will not be able to go too much into comparable work or technical details. I'll talk about qualitative shape analysis, deformation and fracture, and multi-resolution proximity maintenance. And as I go through this, you will see essentially these 3 areas coming in. Topology will come very strongly in the first, physics will come very strongly in the second, and geometry will come very strongly in the third. But really, all 3 come into all of them. And also, these problems that I like somehow fit in the intersection of the continuous and the discrete. They are not purely continuous problems like classical mechanics. They are not purely combinatorial problems. They're somewhere in between. So, and as I go through this, even though these problems will be very different, you'll see a number of common themes, namely that particles interact with their neighbors to some kind of neighborhood shape functions. And this has to be chosen right to make the whole thing work. It's a dynamic setting where samples can be added or taken out. There'll be always strong interest in topological fixtures that appear and disappear. We're going to look at the same phenomenon in multiple scales. And even though we are modeling things in the physical world that are sort of fundamentally continuous, you will see that behind the scenes, there is a discrete structure that tries to capture only the essential changes that are going on in this continuous phenomenon. Okay, let me start with an inverse problem, an analysis problem, with persistence barcodes for shape analysis, where the idea is we're taking a point cloud and trying to understand qualitatively what is the shape. I guess with CVPR going on this week, I'm missing most of the visual people here who might be interested in this. Now, I think most of us are much more familiar with geometry than with topology, and especially if you think about topology as a shape descriptor, well, topology has a good thing, yes? It's kind of, you can take a shape and kind of do various strange things to it, and the topology doesn't change. So it's a robust descriptor. On the other hand, if you're interested in a shape, when you start doing kind of large-scale deformations, the shape is changing, and topology doesn't capture that. So somehow that's the dilemma that we have to deal with. That's one issue. The other is that, of course, point clouds don't have topology. What's the topology of this point cloud? So to really get a space, a topological space, where I can do something meaningful, I have to start building some structure on the point cloud. And the general idea, that's used here is to put little balls around the points. I'm going to use in these examples, I'll show equal kind of radii balls, but in general, of course, you can adapt the size of the balls according to the spacing of the points. And then somehow I'll try to capture topology from the intersection patterns of these balls. And that gives rise to the notion of an abstract, a simplicial complex. So I put my balls on my points, and then I record the intersections. So for example, each of these balls becomes a node, and a pair of intersecting balls introduces this one simplex, and a triplet of intersecting balls introduces this two simplex, and 4 balls intersecting introduces this 4 simplex. Notice, even though I have a 2D point cloud, I'm getting into higher dimensional simplicities. That's the nature of this construction. So here's now my simplicial complex, and this is kind of a nice discrete structure that, under some assumptions, can be shown that somehow captures the topology of the underlying space from which the original points were sampled. And the main tool I will use for understanding topology is this homology, very classical from the 30s. These homology groups, they are vector spaces that capture the essential structure of so-called cycles of all dimensions. For example, if we take a torus, cycles on the torus, actually one cycles, that is cycles of edges, are sort of two types. One is kind of a trivial cycle like this that can be contracted to a point, but then on the torus there are sort of two non-trivial cycles, the one going around the tube like this and the one going around the tube the other way. And so the vector space H1 for the case of the torus has sort of two dimensions. And in general, I'll be interested in the so-called Betty numbers, which are the dimensions of this, the ranks of these groups. And in low-dimensional spaces, these have nice interpretations. For example, beta 0 counts the number of components, beta 1 counts the number of loops, and beta 2 counts the number of voids. So a torus has one component, is connected, has two tunnels, the tunnel like this and the tunnel like this, and then void. But of course, we don't have a torus. We have just this point cloud. And the question is, how do we go from this point cloud to understanding what is the homology, the topology that is, of the underlying space? Well, as I said, the idea is we have to choose a scale and start introducing balls. And of course, we don't know what the scale should be. For example, if I introduce this scale of balls on the point cloud of the previous slide, I get this kind of simplicial complex that doesn't look very much like a torus. It's just a bunch of isolated points and a bunch of edges. And then I get actually in this case 150 components, no tunnels, no voids. As I increase the size of the balls, you can see the intersection patterns become more complex, and actually now everything becomes connected suddenly, but there's still large numbers of tunnels because there are all these kind of wireframe holes, and there's no void. There's no part of space that's enclosed by a surface yet. At this point, I'm getting to roughly to what I would like, namely a situation where I have what I would like, namely one connected component, two tunnels, and one void, and the void inside the torus. But of course, I can keep growing the balls, and eventually what's going to happen is that the interior void will split into many subvoids because the balls start to intersect. And I want to, yes?
Is there a reason why you picked balls instead of, say, something that was anisotropic so that it could sort of lie on the surface and not get big and intersect?
No, that's a very good question. I'm trying to sort of show the simplest possible setting here, where I have isotropic things and the sampling is also, is uniform. But, and I haven't really looked at the issue of anisotropic balls, but I think that can be quite important when you have sampling that's not even. I'm not trying to capture at this point details about the curvature on the torus, but I'll come to this in the next few slides.
I was just thinking, even for detecting topology, if you don't let the balls get big along the dimension, like where the hole is and intersect, then you won't get spurious kind of connectivity across those.
Well, I mean, that's the whole issue. How to get rid of the spurious stuff. That's exactly the whole point. So here, if I plot as a function of the radius of the ball, the beta 1, the number of tunnels that I have, you see I start with no tunnels, then I get like 1, and then I get this large number here because there's all these tunnels. And then at some point I have 2, and then later on, even this one will disappear, and so on. So this brings us to this notion of a filtration. That is, you see, as I grow these balls, more and more intersections come up. That is, more and more simplices go into my simplicial complex. So I have now this set of inclusion maps, starting with the empty simplicial complex, when, say, the ball has radius 0, all the way to the final space at the end. And in the example I was showing, essentially there is a geometric fixture, like the ball size, that dictates the ordering by which the simplices enter the complex. I'm showing here an example from a Morse type of filtration where you can imagine there's kind of mountains and valleys, and then the water is sort of coming down, and then you first see the peaks, and the peaks get larger, then you have the valleys, then the valleys disappear. But what's going on really in terms of the homology is I have this set of inclusion maps on the complexes, and because homology is a functor, this translates into inclusion maps on the corresponding vector spaces. And actually, it's not just inclusion maps, but we know how to follow, in terms of computation, a basis here into a basis there, into a basis there, and so on. So you can maintain compatible bases across the growth process. And here's an example of this. So here is an animation of what I showed earlier, namely the torus being built as the ball radii grow. But then here you see what's happening to the basis element for H1. Oops. So there's more and more of them. There's many, many tunnels, but then as the balls get bigger, they start to cancel out. And eventually, I'll be left with only the two real tunnels that I have. Oops, wrong button, sorry about that. So this brings us to the idea that was published in 2002 by Zomorodian, editor and lecture, that of persistent homology. That is normally, homology is defined as a quotient group of the cycle divided by the boundaries. But the idea is, if you have this growth process, perhaps it makes sense to divide by the boundaries, not at the current stage of the filtration, but a somewhat later stage. The idea is you want to get rid of spurious topological fixtures. That is, for every topological fixture in this filtration, you can think of a birth time when the fixture is born, and then in the future a death time when the fixture dies. So for example, I don't know why that's not showing. If you think about this Buddha model, in many versions the Buddha has little tiny holes that are really artifacts of the sampling. Now, such a hole will be seen when the balls can reach a certain size, because things will connect around the hole, so there'll be a tunnel there. But then pretty soon, because the hole is small, the balls will get larger and they will fill up the hole. So this is a topological fixture that has short life. And somehow the whole notion here is that topological fixtures that live long are the ones that are really real fixtures of the underlying hidden space, the manifold, and the ones that come and go quickly are just artifacts of the sampling and noise and so on. So the idea is to take this point cloud and map it to what we call a persistence barcode. That is just a collection of intervals that indicate the lifetimes of topological fixtures. So here is this structure for the torus. For this point cloud, here are all the intervals that indicate the lifetime of topological fixtures, and for beta 1, for the number of tunnels, and you can see this sort of two long lines. And somehow you see that if you sort of omit the stuff that has a short length, you get something which is really the signature of the torus in the same sense. And that's the whole idea of this approach, that you filter out topological noise because these are topological fixtures that die quickly after they are born during the filtration process. Okay, that sounds good. So now we have a way to try to capture topological fixtures from point clouds. But we're not there yet, because topology is a very weak-shaped descriptor. I mean, topology maybe can distinguish F from A from B. This has one holes, two holes, no holes. But topology cannot distinguish sharp fixtures. Say, cannot distinguish a U from a V. These are the same topologically, or a circle from an ellipse. So the next agenda is to make topology into a finer tool. And the way to do that, there's many ways to do that, but what we looked at is essentially taking the point cloud and from that deriving a different point cloud that somehow has more information, and then applying topology to this derived space. And somehow the intuition is that by computing topology at the whole sequence of derived spaces, you capture something about the geometry of the underlying space. Let me give an example, focusing on tangent complexes. So let's take the U. At every point of the U that's a smooth space, there are two tangent vectors. So I can lift this point into 2 points in the derived tangent space. And there's a projection map from these two down to the original. And now if I look at the fibers of all the points on view, I get two components, because this component, the tangent is going this way, and this component, the tangent is going that way, and these are disconnected. There's no way to continuously go from here to there. So therefore, this kind of lifted space has two components. On the other hand, if I look at the V, if I do the same thing on the V, you'll see I'm going to get four components, because these vectors don't connect with these, because in the tangent space, there's no continuous way to go from there to there. The tangent just points this way and this way. And similarly, this doesn't connect to that. So actually, I get now four components in the V. So by simply looking at this lifted space, I can distinguish the U and the V, even though I couldn't distinguish them in the original space. Of course, that's a trivial example. And what we really do is this. For 3D, we take a space and look at the space of all tangent vectors to it, conceptually. So that's the tangent complex. And now we filter all these new points, that is points plus tangent, by the curvature of the oscillating circle in the plane cutting the manifold along the tangent and the normal. So first points of low curvature come in, then points of high curvature, and so on. Here's an example in 2D to make this clear. I want to compare two things that were the same before, a circle and an ellipse. A circle, of course, in 2D there's only components and holes. If my curvature threshold is too low, there's nothing there, because all the points on the circle have the same curvature. As I raise my curvature threshold, boom, at some point, everything comes in. And so I'm going to get actually two components, because I get, again, the component with the tangent going this way, the component with the tangent going the other way, and I get also two holes, because each of these guys has its own hole. But the ellipse now is different, because in the ellipse there are four stages. If my curvature threshold is low enough, there's nothing there. But at some point, I reach the curvature threshold for these points of the smallest curvature, and then these four vectors appear. And then as I allow higher and higher curvature, these things grow. In other words, I'm seeing now four components, because there is this component with the tangent going this way, this component with the tangent going that way, and similarly here, four components. But at some point, I reach the curvature of this highest curvature points, and then this component join, so two components die and only two continue. While when it comes to holes, there is no holes here, and then at this point also, the two holes appear. Again, I'm going in very broad strokes over this, and there's no time to really discuss details, but I hope this example makes clear what these persistence barcodes capture. I'll just flash a 3D example for the ellipse. I don't have time to go into it. But what I'm really interested in is applying this technology not to ideal shapes like ellipses, but to scan data, like point clouds. So I want to start with a shape and get out a descriptor. So I'm going to take a point cloud and produce such a barcode descriptor. And then also put this descriptors into a metric space. So that's the pipeline I will very briefly outline, and I'll show you only sort of 2D examples because they're easier to show. So the first thing we do is, of course, we estimate tangents. So we blow this up, this point cloud in 1D, into a point cloud in 3D, where the vertical axis indicates the direction of the tangent. And of course, there are two components, because there is the tangent going this way and the tangent going this way. So one point cloud gave me another point cloud. The point cloud of the ellipse gave me these two curves in space. Then I do the curvature filtering. I estimate curvature, and I color my points according to curvature. So basically, points of low curvature are more red. Points of low curvature, of high curvature, they are more yellow. And then I do this filtering process I described earlier. So this is my complex, where essentially I connect things together when they are near enough in this 3D space. It's a bit funny, of course, because I'm summing together kind of Euclidean distance in the underlying space together with angular distance for the tangents in this lifted space, and there's some kind of mysterious constant that you have to choose there. But ultimately, there is such a complex, and as you allow more and more of the yellow points to come in, this complex is evolving, so you can compute persistence. So for the ellipses, here's 3 ellipses, here's what you get for the barcodes. And you can see, for the circle, you do get what you would expect. This is for beta 0, the 2 long lines that capture the 2 holes in the lifted space, and then a bunch of noise things, because maybe these guys join together and form components and so on. But you see here, you start to see 4 components, like we saw in the ellipse example that I showed earlier. And these components become more and more significant the more eccentric the ellipse gets, because it takes longer for the curvature filtering to fill in the ends. And so I can have these point clouds, I can look at this and understand there's a variation here. Or if you want to look at another example, here I have an articulated arm. These are just point clouds. And again, I can capture the variation, and actually I can order this curve saying this is a motion like this just by looking at the barcodes. So that's, in a nutshell, what this approach is trying to do. And also we have this metric on barcodes for defining shape similarity by matching intervals in a standard matching algorithm. I will not spend time on that because I don't have it. So to finish this first vignette, the main point to take home from this is that these persistent barcodes that are kind of qualitative shape descriptors that can be computed directly from the point cloud. I don't have to make a surface and segment it and compute fixtures. You go directly via this machinery from a point cloud to this high-level descriptor, and they capture, and I haven't really kind of justified this fully yet, essential qualitative information about the underlying space. There's still many challenges here. First of all, you have to deal with large data sets, and of course, when you lift them to a higher space, they become even bigger. So there's various techniques to reduce the size of the complex while preserving topology. One has to analyze how stable are these intervals under deformations or perturbations of the shape, and we've done some of that, but not as much as we should. And also notice that this technology that I've showed you, even though it tells you about topological fixtures, doesn't tell you somehow where they are on the shape. There's no association of any location in the shape with a topological fixture, and I think for many practical uses you would need that. But again, due to lack of time, I just want to sort of show, kind of throw out these ideas, and then I'm going to move now to the next vignette unless there's some question about this approach. At the end also. Now we go back to kind of more standard graphic stuff. The idea is to do kind of simulation of deformation and fracture. And again, so we come to some of the points that I mentioned earlier, namely that you're going to have kind of point sampling of both the domain and the interior. You're going to have to do sort of dynamic resampling during deformation, and topology comes in here because you have these fracture surfaces that move through the body, and they can meet each other and merge, and they can split, and all kinds of crazy things can happen. So, that's the kind of thing you can get without fracture, just deformations. Let me kind of briefly go over what's going on here. So what is the elasticity model? Just kind of very lightweight standard continuum mechanics here. So we have the body coordinate frame, and then a deformation is given by a set of displacements on the nodes of the body. So we add u's to x's, and we compute this strain tensor, the Green-Savenan tensor. This is the formula from the gradient with displacement field. And then from strain, we get stress via Hooke's law and the material properties for the body. And then from the stress, we get the elastic force, and then we can do physics. Okay, that's kind of more or less the underlying math for this. But of course, the difficulty is now we're discretizing this, and not in a mesh, but in a set of discrete nodes. So the continuous displacement field U will be approximated by using the values of the field at the nodes interpolated to other points via this interesting and somewhat mysterious shape functions. And I'll show you very briefly how the shape functions are derived. essentially these shape functions indicate the influence of the material in the neighborhood of this point, but it's a kind of more or less standard, moving least squares fit. So the shape functions are defined in terms of certain weights that I'll show you in a moment, and then this kind of standard inverse of the moment matrix, and that's one of the big expenses in doing this kind of point-based simulation, that you have to invert this matrix at every node, at every step. And what you get from this construction is that essentially these shape functions summed over all the nodes at any point of the domain sum to unity. There's a partition, essentially, the influences of all the nodes normalize so that they sum to 1 at each point. And the weight function we use is just a simple polynomial here. And of course, you scale that according to the spacing of the nodes. So each node has a support radius that can vary during the simulation, and that scales the weight function. Yes.
Different nodes can have different radii.
Oh yeah, absolutely, absolutely.
They have a non-uniform distribution.
Absolutely. In fact, it is very non-uniform because the way we started is it's very dense near the boundary and coarser towards the interior. The way the initial distribution is set up, you put an octree, and then you refine the octree towards the surface. And then the initial nodes become the centers of the voxels that are inside the body. So basically, you have very large voxels when you are far away from the surface and very tiny voxels when you are inside the surface. So to do the physics, really the main thing to estimate is not the displacements, but the gradients of the displacements. And we compute that directly using moving least squares. So again, the real loop here is that you have the external forces, and then you integrate forward, get the displacements, you look at the differences, you get the gradients, you get the strain, from that you get the stress, and from the stress you get back to the forces, and now you keep doing that. Okay? This is the basic loop of the simulation. But there are two types of particles. There are simulation nodes, and there are surface particles. And surface particles, you have to think of them as little axes. They have a normal. They point outside, and they are coupled. That is, the motion of the kind of physical particles affects the nearby surface particles, again via the same weight functions. I just said this. Here's another example of an animation computed this way. This has about 200,000 surface particles and less than 1,000 physical particles. So the whole point here is that you have very, very coarse sampling of the interior. You are doing essentially very coarse physics, but for graphics, you are getting some beautiful surface that looks good. So the key points are that you decouple simulation nodes and surface representation. You have a very coarse physical model, but a dense surface model, and this makes the simulations go fast. The previous animation was about 4 to 5 seconds per frame. That's not kind of real time, but compared to finite elements, it's an order of magnitude faster, and it's easy to implement. Now, let me say a few things about fracture. So what if stress goes over some threshold at some point? And actually here, I had sound, but maybe... Anyway, this is just a small example to show what's going on. What you'll see now, these are the physical particles. This is what represents the interior. And what's going on is that as the surface propagates, as the crack propagates through, you are adding more of these physical particles because you need more information in the vicinity where the change is happening. This shows the surface particles. As you can see, there's many more of those, and these are computed based on the positions of the physical particles and each other. And here you can see just the surface particles. That is the representation that then was rendered to give the animation that we saw a moment ago. So the stuff that's interesting here that I'll talk about just for a moment is as all this stuff happens, how do you adapt the shape functions, and how do you decide when to add or to take out samples? The rendering part is also interesting, but I will not talk about it because due to lack of time. So the main idea is that if you have a crack propagating through a material, you want to essentially, for every point, collect its nearest neighbors, because these are the ones that you will interact with. But you want to perform a visibility test, so that essentially the point in the center of the circle interacts with its visible neighbors, but somehow does not interact the same way with its neighbors across the crack. Now that's an expensive computation, and we do as much caching as we can from one time step to another to avoid kind of redoing this visibility test. But there's a fair amount of geometric computation that goes into these visibility tests. Now, if you do this naively, the result doesn't look so good, because I plot down here the weight function around the point, and then I'll show a crack propagating through and the corresponding shape function. If you say 2 points don't interact if there's a crack front between them, if they cannot see each other through the crack front, you get things that start to look like this, and these are very discontinuous and kind of ugly things, which make simulations unstable. So the first thing was to add some more gradual transition from full visibility to no visibility, depending on how deeply the line between the two pixels intersects the crack. So, you know, the standard weight function that I showed you was kind of more or less scaled by this size of the neighborhood of a node. But what we do now is we add an extra term that depends on how far the crack is from the visibility line is from the tip of the front. Effectively, what's going on is that the more you intersect away from the tip of the crack, the longer the distance is between the nodes. So at some point, the nodes stop interacting. So the crack becomes transparent near the crack. So basically, you know, these two nodes here interact quite a lot, even though there's an occlusion by the crack front, but because you are very near the tip, you interact quite a lot. And this binds to continuity. So if you compare what I had before with with the new modified method, you will see that both the weight function and the derived shape function look a lot smoother. So that's one issue to be dealt with. There is sampling. We need to add nodes. Right now, we don't remove nodes. We just add nodes. When a neighborhood becomes too sparse, so what we do is we compute a weighted sum of the weighted of the modified weight by transparency with the weight without transparency. And if that sum becomes too low, we add extra points. So here you have 5 neighbors. Maybe that's OK. Now the crack here comes in, and then the sum of these normalized quantities decreases because omega primed, which is the guy with the transparency, is less than omega. And so maybe now this total sum becomes less than some threshold. So what you do is you add extra points. And so that is why when in the animation you saw these green points being added near the blue points, because the transparency criterion made this node fall below the threshold. Next issue is, how do you really start and propagate cracks? So essentially you compare the largest eigenvalue of the stress tensor against some threshold. And if it's above the threshold, then you start a crack. And you do so by inserting 3 crack nodes. And actually you sort of make 2 surfaces. Each crack has essentially some guy pointing this way and a surface pointing the other way. And that's how you start up. So you have things pointing towards one side, towards the other. And then the crack starts propagating. So so the physics moves these surface particles. But then you pull the first and last back towards the initial surface. And then also because of density, you upsample if necessary. And now you have essentially a larger crack front. And then you have all kinds of interesting topology going on here, because you can go through a material and a crack front can split. And each of them kind of will move independently from then on. Or you can have 2 crack fronts that merge. again, I don't have time to go into this, but it's very...
Or a total of 14 cracks initiate and propagate. 4 cracks in the center merge to form a circular crack front.
Well, I'm almost out of time. Sorry. I showed the animation because they're fun to look at.
Material properties. Our method can also handle brittle materials. The hollow furrow fractures and explodes due to forces acting from the center top of the pedestal. In the explosion of the sphere, the cracks propagate along predefined patterns.
Pre-cut.
By explicitly specifying different stress thresholds, we additionally control the initiation and propagation speeds of the advancing cracks.
And the last one.
Here we have an example of a plasto-elastic object which is deformed beyond recognition before splitting along a complex fracture surface.
It's just slower. And what's neat here is that all those different kind of behaviors come out of the same array. Here's some statistics for the simple example of this twisting bar. So for example, this had 2,000 internal elements, pixels, 30,000 surface elements. During the twist, both expanded. They were both kind of new surface particles, new physical particles, the green ones that you saw coming in. So you went from 2K to 3K, and the surface also, you went from 30K to 45K. Of course, this is more complex than what I showed you earlier, so the time per second per frame is now about 10 seconds on a standard PC. So to finish this, again, the point is there's not tetrahedral meshes here, so also having cracks and so on becomes more lightweight, even though somehow, because we have lots of surface particles but few interior particles, we have both speed and detailed surfaces, but there's still lots of limitations to this. Of course, if there's a lot of fracturing, you keep adding these green things and the number of particles blows up and everything becomes very slow. Visibility testing is still quite slow to know if two nodes see each other across the crack front. You must deal with some topological issues. If you have two crack fronts passing very near each other, you would like them to either sort of stay apart or sort of coincide, because otherwise you have very tiny topological fixtures that cause problems. The method that I described is only first order accurate, so it doesn't preserve energy. And of course, if you're doing real physics, that's a no-no. So that's bad, but maybe for graphics, it's okay. Okay, that's the end of the second vignette. Any question about this? Yes?
To compute the stress, do the particles have a restore rest position?
Yes. And in fact, what happens during plastic behavior is that you change that. So you say at some point, you say, okay, if you kind of deform over some threshold, you change the rest state to be the new state.
So when inserting new nodes, is it easy to assign them their new rest positions? Is there some blended formula?
Yeah. You blend from the neighbors. That's what you do. Yes?
Have you looked into using GPGPU for doing some of those calculations? Because it seems like a lot of this could be applied pretty well to a graphics card, especially doing things like visibility testing and so on.
It's definitely in our plans. We haven't done it, but you're very right. Like this is a very, it's a big loop, it's visibility computation. So it'd be nice to put that, in the GPU. Okay, last vignette to something that is less topological, less physical, but more geometric. I'm interested in the problem of I have moving particles. This comes up in almost every physical simulation as point-based, and I want to know who is near whom. And somehow, if you think about distances, the n-square distances, but really you have only order n independent variables, the positions of the particles. So one should be able to do better. I'm going to go a little bit quickly because I'm running out of time. But of course, I mean, kind of knowing who is near whom is really basic to any physical simulation because fundamentally things interact when they are near. So like in molecular dynamics, you have this neighbor list. You want to know for every atom, all the other atoms within 20 angstroms. For collision detection, of course, you want to know, who is near whom and so on. But the problem is if you have like independent particles or even this kind of fracturing simulations that I showed, things can move independently and they can move a lot. So there can be many proximities that arise during the course of the time that you're simulating. And somehow the goal here is to have a proximity data structure that somehow, even though things move kind of wildly, it tries to be stable. And it tries to be output sensitive, that it only changes as much as the configuration of the system changes. And from this data structure, you can quickly get distance information or collision information. Of course, this is a very old problem, has been dealt in graphics and robotics and many other fields from the beginning of time. And the standard solutions people use, for example, in molecular dynamics, standard solution is voxel grids. You partition space into cells, you keep track of what particle is in which cell. And so when you have to ask who is near this particle, you simply have to search kind of the nearby cells to see who is there. And this works fine if you're interested in a certain fixed scale. On the other hand, in this kind of setting, because you are partitioning the ambient space of the problem, even if there's no deformation, I kind of move as a rigid body, my particles have to be reallocated to new cells at every time step. So you have to touch every particle and do something at every step, even though proximities don't change, even though all the inter-particle distances stay exactly the same, just the translation, this is a lot of work. In graphics, probably the most common method is to use bounding volume hierarchies. I'm not going to go into this in any detail. But of course, for a deformable or for wild particles moving around, the problem now is that essentially you have to recompute and update the hierarchy as the motion or deformation happens, and this can be expensive. So I'm going to quickly go through a new idea for approaching this problem based on a notion that first arose in communications, sort of telecommunications, this notion of graph spanners. So a graph spanner is a way to compress a dense graph into a much sparser graph while preserving shortest paths. And in my setting, I'm going to have particles moving in a physical space. So my dense graph will be the graph of all kind of Euclidean distances. And I'm going to try to maintain only a small number of pairs of edges, pairs of points, i.e. edges, so that from these edges I can estimate all the remaining distances well. So in other words, I'm looking, say, in 2D for a very sparse graph on these nodes like this, with the property that no matter which pair of nodes I take, the Euclidean distance between them is only a little bit shorter than the shortest possible path following the graph. And I call that the spanning ratio of the graph. And what I'll show you now is a way to define such a graph and maintain it as the particles move.
Yep.
Yes?
This sounds similar to the nonlinear dimension reduction things. There's that isomap thing where they have landmark embedding. They form the distances, and then they take a subgraph of that, and they can infer the distances between other ones based on...
John, this notion of spanners is really in many different areas, and there's a huge literature on this. What is novel here is that I'm going to show you a spanner structure that can be evolved under motion and be evolved cheaply. Static spanners, I can give a whole course on spanners, okay? There's just a lot of stuff out there.
I've never heard the term spanner before, but yeah. I'm ignorant. I don't know if they're the same concept or not, but I know a little bit about those papers, and it's...
No, this notion of having a sparse set of distances that captures essentially all distances is in that work. LLEs and so on.
Okay.
So what is the benefit of doing this? The benefit really is that if you have a spanner structure, especially kind of a lightweight sparse spanner, is you can replace a geometric proximity search, like tell me who is within 1 mile of me, by just a graph traversal, which is a very cheap thing to do. Of course, you have to really go out a little bit more because you have this 1 plus epsilon in the spanning ratio. But actually, I'll show you this doesn't make very much difference. So again, the point is we replace a continuous geometric search by combinatorial graph search on the spanner graph. Again, I'm running out of time, so I'll just be very, very brief now. Here is a way to build such a graph, such a spanner that can be maintained over time. Let me just first show you the spanner, the static construction. I'll show by words and then by slides. The idea is you define this notion of discrete centers of radius r, which is a subset of the nodes, so that every other node is within r of one of the centers, but not center is within r of each other. And then you build the spanner hierarchically by constructing, say, first of all, a set of discrete centers of radius 1, and putting in the spanner all the edges between the centers and their covered nodes. And then you double the radius, the r, and compute a discrete centers of the centers, and so on and so on and so on. And at each level, you have the edges from the centers to the covered children, but also, and that's very important, at each level, you connect together all centers that are not too far from each other. And too far is taken with respect to the scale at which these centers were chosen. And it turns out if you do this, this graph will be a spanner. Let me show an example to make this concrete. Here is a bunch of points, and I'm going to choose a subset of them, the pink ones, having the property that every blue point, every other point is covered by one of these balls around the pink points, but no pink point is covered by the ball of another pink point. These are my discrete centers. An important point here is that how to do this has many, many solutions, typically. That's very important, very useful for us. This is not a canonical, not a unique structure. So in this panel, we'll put all the edges between the centers and their covered children. If some child is covered by multiple centers, you just pick anyone. It doesn't matter whom you pick. And then you repeat. You take the first level centers, double the radius, and make centers on those. And now you have these children of the supercenters to the original centers. I mean, standard hierarchical stuff. I don't have to really. And then you do it for one more level, and voila, this is the spanner graph. And also, at every level, and that's very important, you also have edges between centers that are not too far from each other. That is, you connect together all pairs of centers whose distance is only a small constant times the spacing of the centers. And this constant is related to how big that epsilon will be that you have in the approximation of the spanner. Now let's look, and that's sort of the most fun part about this structure, how this can be evolved as things move around. So of course, maybe this node is moving this way, and it's going to move out of the sphere of influence of its parent. But then that's no problem because this guy can take over as a parent. But now maybe this guy is moving out of the sphere of influence of its parent, so it has to be sort of taken up in the hierarchy. It has to become a center by itself. This is all kind of standard data structure type of stuff that you've seen this stuff before. There's nothing very difficult going on. Or you can have a situation where a center moves and becomes within the sphere of influence of another center. That's a no-no. So this guy has to be demoted. And of course, because he's demoted, he orphans some guys who have to be promoted and standard data structuring stuff. Now let's look at the more interesting aspects of the spanner maintenance. Of course, these nodes are connected by some edge. Say at this level, maybe they move kind of more apart, and this edge disappears. That's easy. You have this edge in the spanner, you just take it out. There's only one interesting case in the spanner maintenance, it's this one. These two nodes are too far to be connected right now, but this guy is moving this way, so at some point, according to the rules, they have to be connected. How will you know that? How will you know that these nodes are coming together? In all of proximity maintenance, this is the fundamental problem. It's always easy to keep track of who's near you because there cannot be so many by packing arguments. So if they move kind of more far away from you, that's fine, you can know that. What's hard always is to know who's far away is coming near you because there's too many guys who are far away. That's always the tough problem. And here the hierarchy comes to the rescue. Because before these two guys need to be joined by an edge, at this level, it turns out you can prove in the structure that their parents in the hierarchy are already joined. You have a built-in warning system there's a radar that tells you, hey, watch out, because you may come close together. So basically, the only edges that can come in like this is edges between cousin pairs. Only cousins can be connected. Nobody else can be connected. And that's the beauty of the structure, that there's this warning system. It tells you when two guys come near enough to be connected at a given scale. So, I mean, again, I have to stop almost now, so I'm going to be very brief. But the whole point is that this structure is both dynamic in the sense that you can add and delete nodes in logarithmic time, but also you can maintain it, essentially, as long as the nodes don't move, kind of too far away at each time step. And in fact, how far they can move depends on how up they are in the hierarchy. The higher you up, the more you can move. Then there's a very efficient repair algorithm that will take the new node in new positions and give you a spanner for that. And somehow what makes this possible is the fact that the spanner is a non-canonical structure. I mean, if you care about proximity and make geometry, you can ask me, why don't you maintain Delaunay? Delaunay tells you proximity. Delaunay is fragile. You move things around, Delaunay can change a lot. Because Delaunay is canonical. For a given set of nodes, typically there is just one Delaunay. For a given set of nodes, there's exponentially many spanners. So that makes it possible that when things move a little bit, you may be able to find a spanner for the new configuration that is combinatorially close to the previous configuration. And let me skip the other theory stuff. So one place we use that is for molecular dynamics. So we take proteins like 3-HBD here. Here is the backbone of this protein. And I have added these green edges that make it a spanner with expansion ratio 3. Namely, given any two backbone atoms here, the Euclidean distance between them is no more than 1/3 of the shortest possible path I can find using the red and the green edges. And again, I just want to show you this animation. Here is a very simple MD animation. I stopped it. Here you can see a number of types of edges. Green edges are edges that came into this time frame. Red edges are edges that will die in the next time frame. Gray edges have been around. And I hope what you see here is this, that even though this is doing some pretty wild deformation, most of the time you see gray. That these edges stick around. The spanner is a structure that somehow behind the scenes is stable, even though the motion itself looks very wild. And in fact, if you look at the statistics, what's happening is that for every 100 MD steps, you roughly change about 2 to 3% of the spanner. It's a very stable structure, even though to us, the motion looks very wild. I have out of time. Let me skip all this other stuff, other goodies that the spanner can do. I kind of like this quote. I don't know, have you seen this old movie with Burt Lancaster, The Leopard? It was based on this Italian novel from the last century, from the 1850s, the Risorgimento, the time that Italy became a unified nation. And it's about Sicily and about the politics of Sicily. And it says in Italian, tutto cambia perché nulla cambia. That is, everything is changing so that in the end nothing changes. And it's a famous quote in Italian politics, but I think also it applies here, because somehow everything is changing, but underneath, very little changes. Anyway, I think I've taken over my time. So here is, again, a summary. These are the 3 vignettes I talked about: qualitative shape analysis, deformation and fracture, multi-resolution proximity. Here are some of the tools that went into this. Some other work I didn't talk about that relates to point cloud, like putting together scans without any help. Just you take the partial scans, boom, you put them together. You can take partially scanned shapes and a library of existing shapes and complete a shape. We can do segmentation of point clouds. Also, we can do wide area contact between deformable bodies, but I will not talk about any of this. I come back to these common themes. Particles interact with their neighbors through shape functions. We do resampling as necessary. Throughout, we pay attention to topology and the destruction and creation of topological fixtures. We look at a phenomena in multiple scales, and then somehow always behind the scenes, behind this continuous behavior, the discrete structure that captures its essentials. And I just put this quote from Heraclitus here, one of the pre-Socratic a philosopher that tries to say, even though those things look they're different, actually they're the same. I'd like to end by thanking my students, postdocs, and collaborators, and then also the funding agencies. As Hughes mentioned at the beginning, I'm doing work on sensor networks. You may say, what does it have to do with sensor nets? Actually, it does, because sensors are just nodes in space. And if I want to understand the structure of the sensor layout or the structure of a signal landscape, then I get into problems that these techniques that I've talked about can be applied. For example, I may want to find boundaries of a sensor field, or I may want to find sort of nice routes in the sensor field, and all those things actually are like finding a curvature on point clouds. So you know, I mean, maybe that should be a different talk, but I want to just make the point that even though those things look different, actually there's some shared stuff, and I'll stop here and take questions. Yes, John.
You maintain your proximity structure.
Yeah.
Are there any scenarios under which bad things can happen, and it's sort of either say it fails to be a good structure for finding nearest point queries or something like that?
Yeah.
Just always
No. Here is, I mean, of course, I gave you the selling point, right? It's something I don't fully understand yet. This structure is extremely good when you have large-scale motion. And mostly we tested it in the context of molecular dynamics. So when you have an unfolded shape that wanders through space and starts to fold, it's extremely efficient in the early stages. And then you have the end game, when you're almost packed and you sit there shaking, okay? You see, now what's going on is that all this shaking is really causing lots of changes in the low levels, in the bottom level of the spanner, and it's expensive. And actually, in that case, the fixed voxel grid is better by a factor of 2 or so. So somehow, you see, in simulation, you always have this Eulerian versus Lagrangian methods. And my feeling is that what has to happen here, and I don't know how to make it happen, is that the spanner is a structure affixed on the object. The voxel grid is a structure affixed to the ambient space. Somehow, in this molecular dynamics problem, I would like to start with a structure that lives and follows the shape, such as the spanner, and at some point I want the structure to jump off the shape and stick onto the ambient space, to go from being Lagrangian to being Eulerian.
What are you talking about time? It could be different. In some parts of the space, maybe you want...
Right. So maybe some part of the space can be affixed to the object, some parts of the space can be affixed to the ambient space, or maybe in between, whatever that means. I don't know, but I'm wondering about this. So yes, if you have things that mostly stay put but shake a lot, it's not good. This is really beautiful for large-scale motions.
Do you use the spanner data structure for your simulations in Meshless?
No, these things happen concurrently. So the collision detection that's going on in the fracture, shame to say, is ax-aligned bounding boxes, because it was the easiest thing to implement.
What about just the proximity to know which points are your neighbors? That just...
Okay, what's going on there is there's actually 2 versions, whether you have only kind of moderate deformations or extremely large deformations. In the moderate case, you cache, so you pre-compute in advance where your neighbors, and more or less you update this. And the updates are small because basically only where there's cracks there's some update going on. And the other neighborhood relationships you assume are kind of fixed.
Well, what if there's resampling changes because there's an area of high deformation?
Right, so for high deformation, we put a voxel grid. Ease of implementation and SIGGRAPH deadlines take their toll, okay? But that's the truth, okay? And you had a question? Yeah.
Sorry, I missed it. Just running the algorithm to construct the spanner, the first level spanner, is a global algorithm or actually distributed?
Actually, it is distributed. I mean, we have a paper that shows that it can be done in a distributed way, because this algorithm is interesting when you have multiple, moving vehicles or moving nodes, and you want to maintain.
Only if you require, for example, its neighbor information.
Yes. Yes, paper about this. That will appear actually next week.
Okay. The reason I ask this is because I just, since you mentioned about sensor network, have you considered apply the spanner techniques for example, to build a cluster in sensor network or find the cluster height, that kind of thing. For example,
I have done work in computing clustering in sensor networks. I haven't used the spanner because at least today most sensor nets are not mobile, nodes are static, and the main point of the structure is to maintain proximity under motion. But it's a very simple thing to do when you have, say, moving cars or airplanes. In fact, the first picture I put up, I don't have, I mean, in fact, you know, we tried to show earlier was from a simulation of the US airspace during, I think, July of 2 years ago. Where is that? And maintaining proximity among the aircraft. Where is it? I flashed this quickly. Yeah, this background image. These actually are airplanes flying over the US, and the color indicates the level at which they are in the spanner hierarchy. And this indicates the worst case. That is, here's a node at the highest level, and this is how many other essentially planes it has to be in contact with to maintain proximity information. Almost all nodes have nothing like this. I mean, have just 3 or 4 in their neighborhood. But this is the worst case. So I think this structure has some merit for this kind of application where you have mobile. And actually, I mean, this falls in the framework of something I call kinetic data structure, something I talked about here actually like 5 years ago. But this is the first KDS I can do in a distributed fashion. And it's much harder than doing it in a kind of standard sequential function, because somehow the whole idea is you can detect when something goes wrong and repair it locally. But if things are going wrong simultaneously in many places, then you have to argue that these repairs don't have adverse effects on each other, and that is not easy.
Yeah, why should spanners be good? I mean, I can see why spanners are a great idea if you have points that tend to move
exactly
with each other.
Right.
You have planes that are just, that have, well, I suppose when they're coming into an airport, I guess they start tracking each other, but most of the time, the planes, if they happen to be near each other, it doesn't mean they're traveling with the same velocities, the same direction.
Right. I didn't show this, but one can do these things in higher dimensions. For example, instead of building proximity structures in real space, you build proximity structures in a space that includes position and velocity. And then you only link things that move near each other and in the same way. So if you do that in the plane case, essentially, you will sort of cluster the eastbound flights from the westbound flights, from the northbound flights, from the southbound flights. And you have plus and minuses. I mean, you lose something, you gain something with all these things. But even if you do the clustering, I mean, the hierarchy in the real space, the cluster is still very good for the airplane case, actually. I mean, you only maintain on the average maybe about 10 other planes, and they're mostly kind of near you. So it's really very lightweight. Okay. Thank you.